Hi, I'm Jonah Leibniz. You see me as such fine quality chemistry educational videos as The Lab's on Fire Again! And Honey, the tackle box just ate the kids. Today we're going to be looking at percent dissociation of weak acids and weak bases, because what I'm going to show you here, I'm going to work with acid, a weak acid like vinegar, but this also applies to weak bases as well. It's the same idea. But first off, we have to say, what is dissociation? Well, dissociation means breaking apart. Okay, you have strong acids, strong bases, weak acids, weak bases. Now, the thing is about the weak acids and weak bases is they do not dissociate very well. In fact, they dissociate or break up in the water less than 5%, whereas the strong acid and strong base, they break up 100% in water that they dissolve. So weak acids and weak bases are more true to themselves in that sense. So when we talk about can a weak acid hurt you? Yes, if it's concentrated enough, it can very well hurt you. Okay? So let's take a look at this one. So here's our problem. We have percent dissociation of 2.5 molar of vinegar. Okay, the HC2H3O2, and there's given our equilibrium constant, our dissociation constant for acid, if you will. It's the same thing. It's still the idea about equilibrium. So let's go ahead. We know this is a weak acid. Okay, we have a clue that it's an acid because it's giving off a proton. So let's go ahead, let's just set this up. So we assume that it's going to be in water plus HC2H3O2. And it is at equilibrium, so it's going to go back and forth. And then we get H3O plus C2H3O2 with a minus charge to it. So we're going to need to do an ice table to figure this one out. Okay, find our equilibrium concentrations. Okay, so we can go ahead and do that. I do not need to worry about the water because it doesn't contribute anything. So we're going to have our initial, our change, and our equilibrium. So we're going to go ahead and we're just going to draw this across like this. Okay, and they told us it's 2.5 molar. Okay, so it's 2.5 molar. Now the initial values of these is going to have to be 0 molar because nothing has started yet with our chemical reaction. So we have only this, we just dumped it into water, and then we're going to check it out at some point and see where is this happy equilibrium coming to. So our change, that will mean that there's going to be a minus x here. We don't know how much it is. Now we're also assuming that the x is going to be small as well. That's going to make things a little bit easier. So we look at that, and here we say 2.5 minus x. Here is x and x. So those would represent our equilibrium concentrations. I just simply went and added it down. That's all I did. But now we have to go and say, all right, we're assuming that x is small. If x is small, then we can go ahead with our equilibrium, acid equilibrium, or acid dissociation constant. Remember, it's going to be the products over the reactants, okay? And it's the concentrations, right? That'd be kind of important. Now, everything turns out in the original equation to be 1 to 1 to 1 to 1. Yay, that makes it a little bit easier because we don't have to square anything and all that other wonderful stuff. So let's go ahead, let's plug in some numbers, shall we? So I know that the acid dissociation constant, they gave that to us in the problem, 1.8 times 10 to the minus 5th. Okay, so it's going to be 1.8 times 10 to the minus 5th is equal to, well, what's the concentration of our products? Well, it's going to be x times x, or x squared, right? Divided by, now we assume that the x here is going to be really small, so it really shouldn't be affecting the 2.5 that much, so that's why we can go ahead and eliminate that and put the 2.5 down here. So this is what we have. This is our constant. This is what we've got. Okay, And now we just got to solve for x. So we can multiply both sides by 2.5. Okay, we can multiply both sides by 2.5. So 2.5 times 1.8 times 10 to the minus fifth is equal to x squared over 2.5 multiplied by 2.5. And as you know, this is going to cancel out. Okay, so we move on to our next step. I'm going to shoot that off in red. And the bottom line is, ladies and gentlemen, once we have all that figured out, x is equal to 6.71 times 10 to the minus third molar. That's our equilibrium concentration for that. Okay, now what about the percent dissociation? I was going to spare the time and not do all the math that's necessary for it. Okay, so now I can go ahead and do this. Well, percent dissociation, it's going to equal, well, let's take a look. We had our, oh, we don't have the formula up here. That's okay. It is our equilibrium over the initial. So it's the equilibrium of our H3O, all right, over our initial of our acid, okay, HC2, H3O2, times 100. So that's what the formula will look like. So that's what they mean by the equilibrium divided by the initial. Now, since our equilibrium is really, really small, right? So let's go ahead and finish this off. So I know that 6.71 times 10 to the minus 3 molar divided by 2.5 molar, okay? We're going to multiply that whole number by 100, and we're going to get 0.27%. I rounded to the second decimal place on that one. But that is our final answer. So our vinegar, our acetic acid, if you will, at 2.5 molar, it only dissociates 0.27%, which definitely falls into the less than 5% category. So yes, it is a weak acid, and it has dissociated at 0.27%. Hey, I hope this video helped you guys out, and take care, and I'll see you all the next time.